Thank you very much, Professor Yong Cheng, and it is a great pleasure to be able to speak in front of the Chinese audience. It's the second time in my life and the second time in the last 2 weeks that I'm speaking for audiences in China, and 2 weeks ago it was for Huawei company that I gave a lecture. So the subject of my talk, I will try to introduce the subject I'm involved with for the last several years, and somehow illuminate the origins of this approach to proof theory and somehow the main problems and goals. And so it will be the results I will be talking about will not be really very fresh, but nevertheless, exposition of these ideas evolves and becomes better and better in my opinion. So I will try to present it now. Okay, so let me begin by recalling that mathematical logic, one aspect of mathematical logic deals with the study of formal systems that are sufficiently strong to formalize significant parts of mathematics. And in the course of, let's say, the last 100 years and more, there were several such systems, standard systems developed in mathematical logic. Among them, those three particularly important ones that deal with, firstly, so-called finitary mathematics, or mathematics of finite objects, or as every finite object can be coded by a number. So this is usually formulated as a theory of arithmetic. It's called piano arithmetic. So that's the schematic theory of natural numbers in the language with plus and times. Then there is the second order arithmetic, the system which was developed to formalize analysis or the theory of real numbers and functions. So this is a extension of piano arithmetic by variables for sets of natural numbers. And in full second order arithmetic, we assume the schemata of full induction for formulas expressible in this language for numbers, and comprehensions, formation of sets by arbitrary properties expressed in this language. And then there is this well-known Zermelo-Fraenkel set theory ZFC with the axiom of choice that is believed to formalize practically all conventional mathematics. It is based on the abstract concept of set and memory. So these are the three main, so to say, cornerstones of formalized mathematics as seen in mathematical logic. And of course, as a side remark, these formal systems are now being developed as purely theoretical devices. Now they are materialized in some sense in various automatic and interactive theorem provers such as Koch, Isabelle, and others. Okay, so what we see that logical theories such as those above, they greatly differ. They differ in several aspects, and for example, they firstly differ in the expressivity of their languages, or as one calls it in logic, richness. So rich languages can express more, whereas weaker or poor languages can express less. So the language of set theory is richer than the language of arithmetic, and even than the language of second order. However, being able to express more doesn't mean that your logical system is able to prove more facts. So this property of being able to prove more is called the strength of a logical system. So essentially it corresponds to the amount of axioms or the number of assumed principles or axioms for the system. And theories, even in the same language, can differ in strength. But then there are other parameters that are relevant for the study of axiomatic theories, especially in connection with the systematic theorem. For example, the speed of proofs, the length of proofs, the particular deductive mechanism, which rules are used and how. So all this, the study of these aspects and comparison of various systems is the main subject of proof theory. It's a theory which studies axiomatic systems and proofs in them. So for many years, since the work, essentially the work of Gensen, proof theorists have been looking for ways to compare and measure proof theoretic strengths, somehow to relate to each other, to one another, different formal systems, and to develop some kind of quantitative, perhaps, measures of their strengths. And this topic is called ordinal analysis because mostly people concentrated on various measures of strengths related to the notion of ordinals. So ordinals or well orderings are the objects that can be associated to formal systems to measure their strengths. Okay. Now, in my talk, I will begin by, let's say, saying that what kind of make another remark that it's not only the role of ordinals is not only to compare the strengths of theories, although that's perhaps the most straightforward use of them. So usually the way of analyzing a formal system yields more interesting information about it. So for one such piece of information that people were interested in are, for example, so-called provably recursive functions, computable functions that can be proved to be total in a given system, and closely related subject of explicit combinatorial independent principles that can be found or formulated for one or another system. So these are the topics tightly connected to the general question of analysis of a given formal system. And what it can deliver, I will demonstrate by the so-called worm principle, which is a representative of a much larger family of combinatorial results that can be proved to be independent of piano arithmetic in this case. It all started with the work of Paris, Kirby, and Harrington in the late 70s, who found the first and very interesting examples of such principles. The particular example that I'm talking about here was found by Hamana and Okada in 1997, and I discovered it independently, but later in 2002. So it deals with the particular game to be played on words in the alphabet of natural numbers. So suppose, so we consider finite strings of natural numbers, which we call words or worms sometimes. So words will be denoted by Greek letters, such as alpha, and we can say that define the notion of a word alpha to be higher than n, than the natural number n, if each letter of alpha exceeds n. And then, given any word alpha, we can generate the following sequence of words according to the following rules. So first, we start with the word alpha, And once alpha k is defined, we define the word alpha k plus 1 by the following rules. Firstly, if alpha k begins with 0, then alpha k plus 1 is obtained by deleting this 0, the head of the long worm alpha k, as we consider. And then if alpha k begins with any letter larger than 0, letter n plus 1, then we should do the following. We should find the longest possibly empty prefix beta 0 of the word beta. Can you see my pointer as I'm pointing it? Yes?
Yes, I can. We can see.
Okay, very good. So we should find the longest possibly empty prefix beta 0 of beta, which is higher than n. So we read our word alpha k from left to right and stop at the very first letter, which is smaller, which is at most n. Assume this word beta is written as beta 0 gamma. Then the next word alpha k plus 1 will be will look as follows. So we take lower the head n plus 1 by 1. So we obtain the word n beta 0. We iterated k plus 2 times and applied, and then this prefix will be followed by gamma. So in some sense, n plus 1 beta 0 will be replaced by this long expression of k fold, k plus 2 fold iteration. So these are the simple rules of the game. And then an example that I would like to demonstrate is this one. So suppose we start with the word alpha 0, which is this one. Then what will be the next stage? So here the head is this letter 1. The prefix that I'm talking about will be the 2 letters before the 0, which is the first letter below 1. And then we should repeat it 2 times because it's the first step of our game. So we obtain the word 0303022. So the rule number 2 was applied to alpha 0. Then we see that the new word begins with 0. So at the next stage, this 0 disappears, is deleted. And then again, we are in the situation that the word begins with 3. Then what should we do? So this prefix that we talked about is now empty because the next letter is just 0. So 3 becomes 2, and it is repeated now 4 times because now we are at the stage 3 of the game. Okay, and so on and so on. So we obtain the word, similarly, we obtain the word alpha 4, where we have 1, 2, 2, 2 repeated 5 times. And alpha 5, where we have this whole prefix repeated 6 times, and so on and so on. So it appears initially that this word is growing and growing. However, the result is, in fact, that the following statement called WP, worm principle, is true, however, unprovable in piano arithmetic. So, in fact, for each word alpha, the sequence alpha k terminates in an empty word. So the process that I have just described is always finite, and this is a statement of the worm principle. And as I mentioned, the most interesting aspect of it is not so much that it actually is true, but rather that it is not provable in piano arithmetic, or as I mentioned, by finitary means. So any proof of this mathematical statement, WP, must, according to the theorem, use methods not formalizable in piano arithmetic. And that's already a pretty significant statement, because we know that a great many mathematical results, especially dealing with finite combinatorics, they all are formalizable in PA, in contrast to this one. So we may ask, what are the reasons for this WP to be true? As far as I know, there are 3 different arguments for it. They're not difficult, I will omit it. The most traditional kind of argument would be to assign ordinals to these objects, to worms, and check that the rules of the game, they lead to the decreasing of these ordinals. And as we know that there are no infinite descending sequences of ordinals, that would mean that WP should be in fact true. Okay. Moreover, we can say that WP is a kind of Gödelian type of statement, in the sense that it is equivalent to the so-called sigma-1 reflection principle for piano arithmetic. I will explain later in my talk what it means. So far, you need not be aware of it, but that's you can just for now it will be sufficient to know that this is a kind of statement generalizing Gödel's consistency assertion for PA, an independent sentence for piano arithmetic. But the third point is can be easily understood right now, is that we can associate with this statement the following function, the function f of alpha, that associates with the worm or with the word alpha the number of steps of the game until the word alpha n becomes empty. So the f of alpha is a minimal natural number n such that alpha n is empty. In other words, the length of this game. The third statement states that this function f of alpha exceeds any function, any computable function that can be proved to be everywhere defined in piano arithmetic. So that's the essential property of this construction. So now it is interesting that these statements appeared, at least in my work, not as an ad hoc statement, but rather as a result of abstraction from certain properties of reflection principles mentioned so far, certain properties of piano arithmetic that came out of its analysis, way of analyzing piano arithmetic. And I would like to explain some ideas behind it. So it's not accidental that this statement holds, but rather it is a kind of representation of certain properties of piano arithmetic, that of certain combinatorial, if you like, aspects of the proof theory of piano arithmetic. Okay, so that's kind of illustrative example, but let me now add a few more slides of background on arithmetic, because it will play a role in what follows. So what is piano arithmetic? So we work in the first order language, or first order logic, where the language consists of two constants, 0 and 1, functions plus and times, and the third function 2 to the x, exponentiation, as well as predicate less than and equal. So this is the standard signature of formal arithmetic, extended for convenience by exponentiation, which allows us to not to bother much about let's say, overcome initial difficulties of coding. So this language has an obvious interpretation in the standard model in natural numbers, and that's the standard model of arithmetic. Now we introduce the following notions. Bounded quantifiers are quantifier occurrences in logical formulas in this language that are bounded. In other words, quantifiers restricted by terms. So if a quantifier for all x occurs in the context for all x smaller than t, where t is a term expression involving plus, times, and explanation, then this is a bounded universal quantifier, and there is x smaller than t, where t is a term, then this is a bounded existential quantifier. Formulas in which all quantifiers are bounded are called also bounded formulas, sometimes delta naught of x formulas. So these are, in some sense, very simple kind of formulas expressing all properties expressible by such formulas are decidable, right? So one can check whether such a quantifier holds is true or not true using finitely many steps. One first computes the value of the term t and then checks whether the quantifier is whether the property holds for all x smaller than that number or not. This is decidable. So nothing uncomputable is expressible by bounded formulas. And elementary arithmetic is the formal system which has certain standard minimal set of basic axioms defining plus, times, exponentiation on all symbols in our signature, plus the induction schema for bounded formulas. So that's called elementary arithmetic. Whereas in piano arithmetic, we allow arbitrary formulas expressible in our language, also with unbounded quantifiers, together with in the induction formula. So piano arithmetic can be seen as an extension of AA with full induction, where phi is any formula possibly with parameters. So that's two basic formal systems that we deal with. And we also need a few to say a few words about formulas with unbounded quantifiers. As we all know, every logical formula in first order logic can be brought to an equivalent Frenex normal form. That is a logical form where all quantifiers stay outside. So it begins with a prefix of unbounded quantifiers followed by some formula which can even be assumed quantifier free. In the language of formal arithmetic, one considers the following classes. So as a minimal class of formulas, which is denoted sigma 0 or pi 0 or delta 0, one considers bounded formulas. And then adding quantifiers, unbounded quantifiers on top of bounded formulas yields classes of sigma n formulas or pi n formulas. So sigma n formulas are formulas where this block of there is a block of n alternating quantifiers followed by a bounded formula. Pi n formulas are those where there is a block of also n alternating quantifiers but in a different order. For all exist, followed by a bounded formula. So these are the formulas of the so-called arithmetic hierarchy. And the most important fact about it, both practically and philosophically, is that predicates definable or sets definable by sigma 1 formulas are precisely exactly the recursively or computably enumerable sets of natural numbers. So a set is computably enumerable even only if it is definable by a sigma 1 formula. So that shows since we all know that computably enumerable sets are as basic as computable functions, computable partial functions, so that's another reincarnation of the notion of computability in the context of arithmetic. And this is a very robust and important class of sets or predicates or of functions. So are sigma 1 formulas. So sigma 1 formulas in the standard model are essentially programs to compute something. They are equivalent to Turing machines in the context of arithmetic. So therefore, it's no surprise that the notions of sigma 1 and pi 1 and of course related classes sigma n and pi n play a very big role in the study of piano arithmetic. So one can restrict induction schema in PA to those classes sigma n, and then one obtains the hierarchy of extensions of elementary arithmetic, usually denoted I sigma n. So this I sigma n is the elementary arithmetic plus induction schema for just sigma n formulas. So if one is thinking about induction for enumerable predicates, then this system is called I sigma 1, perhaps the most popular example. All such systems are known to form a strictly increasing chain. So the union of this chain will be piano arithmetic itself, because as I said, every formula is equivalent to the sigma n formula, so logically, so full induction is equivalent to sigma n induction for each n. So that's the background in arithmetic I wanted to start with. And then I will go back from technical back to historical part of my talk. So I would like to connect it with the ideas of Gödel and Turing. So let's recall the incompleteness theorem of Gödel. Namely, we are more interested in the so-called second incompleteness theorem. So it's useful to introduce this notion of a Gödelian theory, which perhaps is not the standard use of words, but nevertheless, for this talk, I prefer to use it. So let's call a theory T Gödelian if it satisfies the following first order theory T. If it satisfies the following conditions. Three main conditions are conditions of Gödel's incompleteness theorem. So firstly, we assume that the natural numbers and operations plus and times are definable in T. One can assume that they are just part of the language of T, if the T is in the language of arithmetic. One can also, if we want to be more, if our results to be applied to larger classes of systems, we can assume that these operations are definable in T in terms of relative interpretation, for example, no matter what it is. Secondly, we assume that a Gödelian theory proves basic properties of some basic properties of these operations. For example, it is sufficient to assume that it contains the axioms of elementary arithmetic. It's a pretty weak assumption. And then the third requirement is perhaps the most significant one, is that there is an algorithm, or equivalently a sigma 1 formula, recognizing the axioms of your theory. So your theory has to have a definable set of axioms, and here we of course assume that the formulas of the language of T itself are, we think of them as strings of symbols. These strings of symbols are coded into the language of arithmetic using some standard Gödel numbering, one of the standard systems of coding that allows us to do so. For example, even if, whereas in the time of Gödel, that might have been one of the greatest ideas in the proofs of his theorems, to the introduction of this Gödel numbering. For us nowadays, we of course know such systems from our computers, and it does not surprise anyone that whatever we do with symbols, we can do with numbers. So that's such a representation is assumed. What is important that the set of axioms of the theory T is assumed to be computable, or at least computably enumerable, C1 definable. So these are the requirements for systems that we deal with. And then, as Gödel has shown, given such a system, one can write out a sigma-1 formula denoted box T of X, which expresses in a natural way the property that X denotes the Gödel number of a formula provable in theory T, so-called probability predicate. And writing the formula not box T falsity, for example 0 equals 1, we obtain the formula expressing consistency of our formal system T. T is called consistent if contradiction is not provable in T, and this fact that T is consistent can be expressed using the probability predicate in a natural way. So we denote this formula con T. Gödel theorem then tells you that if a Gödelian theory T is consistent, then the formula con T is true but unprovable in T. So that was the first and the main example of a true unprovable statement in formal arithmetic that Gödel discovered. So that's the content of Gödel's second incompleteness theorem, essentially. So that was proclaimed by Gödel in 1933. Soon it was published, 1931, soon it was published, and then immediately logicians started exploring this new phenomenon of incompleteness that was discovered by Gödel. And one natural response to it that comes to mind to everyone is the following one. Okay, so the formula con T, consistency of T, is not provable in T itself. So what if we just add con T as a new axiom to our system T? After all, if we are using the system T, we sort of believe that it is consistent, so we can add consistency as a new axiom. Will the resulting theory be complete now? Maybe it's enough to add just one sentence and obtain and overcome the Gödelian incompleteness here. However, the answer is obviously no, because the system T1, T plus con T here, is in fact also Gödelian. If T satisfies the three assumptions, then T plus yet another axiom will satisfy them too. So let's see, natural numbers are still definable. T proves basic properties of these operations. So this property does not change if we increase our theory, right? If we strengthen it. And still there is an algorithm recognizing the axioms of our system, because we just ended one axiom, so our algorithm we add to our algorithm just one more case to consider. particular formula conti. So the answer is yes, the theory T plus conti is Gödelian, and therefore it is incomplete. And then Turing suggested to continue this process. In fact, it was not Turing who suggested it. Probably it was suggested even earlier by Church and Kleene, and Turing, who just came to Princeton to study, to do his PhD under Church, took this problem as his project. Turned out to be a very large and important study. However, it is not so well, it is pretty well known today in the area of computability because of one particular paragraph there, where Turing essentially introduced so-called oracles and oracle computations. However, for proof theory, this paper plays a much, I would say, also a very significant role, although it is technically much more involved and, in fact, I would say goes much deeper. So let's see what was this suggestion. So we start adding consistency to our theory. So we start with particular theory T0. Then at the first iteration, we add consistency assertion. Then we obtain a theory T1. It is Gödelian, so its consistency for T1 is not provable. So we obtain T2, which is written here. And we can inductively go on and go on. So we obtain the theory Tn plus 1 by adding consistency to the theory Tn. And obtain this infinite ascending sequence of extensions of T. Then again, the same question: is the union of Tn complete? Now complete. Maybe adding omega many new statements would yield us a complete theory, and the incompleteness will be overcome, so to say, in the limit. But unfortunately, the answer is again no, because even though the theory T omega, the union of Tn, is infinitely axiomatized now, still it is still Gödelian. Because why? Because there is an easy algorithm generating the new axioms for Tn, right? For T omega. So the sequence conti of plus conti and so on, it's just iteration of one particular construction, the construction of the formula con. In terms of Gödel numbers, if you like, or in terms of strings of symbols, that's a very easy iteration of a particular string. So it is computable. This sequence is computable. And as we know, the set which is generated by a computable function, the range of a computable function is computably enumerable. So we see that this set of axioms at least is computably enumerable. It is in fact computable because the sequence increases in the formulas con Tn, they're strictly increasing in their length. So this is all computable. So the theory T omega is Gödelian, and we can start the same process from T omega onwards and obtain theories T omega plus 1, T omega plus 2, and so on and so on and so on. And so here I depicted somewhat graphically how it sort of looks like. So we start with a theory T0 and go right in the right direction by adding new axioms. So we obtain firstly an infinite sequence, then there is a limit of this sequence, and so on, another sequence, and this goes on and on. So that's this process is called is nowadays called the Turing progression. Sometimes Turing-Pfefferman progression. The name of Pfefferman. Pfefferman studied these progressions 20 years after Turing, whose work was somehow abandoned for several decades afterwards. Okay, so that's how it looks like, and it appears that this process, so to say, never ends. But it has to end, right? So there are obvious reasons for it to end, because let's say our theories are Gödelian, they are computable, so in particular they are countable, right? And certainly we cannot obtain uncountable sequences of uncountable lengths in this way, because to do so we would need to be able to arithmetize uncountable ordinals, which is not possible in arithmetic. So there are obvious bounds to the length of this. However, looking in details on how far it goes, yields that there are multiple problems associated with this construction, and Turing dedicated his thesis to this problem, to the study of this problem. In fact, it is interesting that Turing wasn't studying this process just for the reason, just for fun. In fact, overcoming incompleteness wasn't so much his intention, as he writes in this paper the following. So he actually wanted to obtain a classification of arithmetical statements according to the stages of this process. So he wanted to use these theories, T alpha, as a kind of measuring stick to measure the strength of logical theorems. So that's how he puts it in his paper, published in 1939, System of Logic Based on Ordinals, in Proceedings of London Mathematical Society. So he writes, we might also expect to obtain an interesting classification of number theoretic theorems according to depth, in quotes. A theorem which is required an ordinal alpha to prove it would be deeper than one which could be proved by the use of an ordinal beta less than alpha. However, this presupposes more than is justified. So this last sentence that I painted in blue needs some explanation, and that's what I'm going to do in my next slide. But basically, so here he very explicitly formulates his intention. He really wanted to obtain a certain classification and measure logical theorems, arithmetical theorems, number theorems, according to how far they are from, let's say, piano arithmetic in this process, something like that. Now, why does this presuppose more than is justified? This is due to the difficulties and very serious ones that Turing encountered. In fact, the difficulties are, as we now realize, there are two kinds of difficulties here, why such a classification would be problematic. The one is relatively simple, however, substantial but simple, and it was, let's say, discovered by Pfefferman. So there is this logical complexity restriction. I will explain it in a few slides later. The second difficulty is still a difficulty today, and it is called the problem of canonicity of ordinal notation. So that's the first time in history that where this problem appeared in the essentially explicit form in a paper. So that essentially one can say that this problem was discovered by Turing. Okay, so what is this problem of canonicity of ordinal notation? So as I mentioned, in order to formulate theories T alpha, one needs to fix their probability predicates, or at least the formulas expressing their consistency, because it is these consistency assertions that form the axioms of later theories. So, in fact, what we seem to be defining by transfinite induction here on alpha is not the theory T alpha itself, but rather its consistency assertion. Now, consistency assertion is an arithmetical pi1 formula, and in order for it to be so, one needs to have arithmetical representations of ordinals at our disposal, because without having alpha or some notation for alpha or some arithmetical formula defining alpha, we will not be able to even state what does it mean to say that T alpha is consistent. So this is certainly needed, and all constructions of T alpha should start somehow with a representation of ordinals here. Now, ordinals can be represented in arithmetic in various ways, and one of the ways that was already known by the time of Turing work was developed by Kleene and Church, the so-called Kleene system of ordinal notation O. There one assigns numbers to certain to specific ways of let's say one assigns notations to certain initial segment of ordinals, so-called constructive ordinals. And this can be done systematically in such a way that every ordinal that has a notation will eventually have a notation in that particular system. For the purposes of Turing project, so Turing also used it and Pfefferman used it. However, for the purposes of dealing with it, it is not even necessary to use this specific system of notation. For example, if one is satisfied to having sufficiently large initial segments of this sufficiently large transfinite sequences of these theories, of these progressions, one can use a simpler idea. For example, one can say that one can use the fact that every countable ordering, or every countable well ordering in particular, is embeddable into the ordering, into the linear ordering of rational numbers. So for every countable ordinal, one can find a subset of rationals which would be isomorphic to this particular ordinal with respect to the standard restriction or the standard ordering on rationals. So fixing a system of ordinal notation is, for example, equivalent to just fixing a subset, a particular computable subset of the rational number. So in fact, when I draw for you this picture of the ordinal omega squared, essentially, you can realize that the points that I selected here are in fact certain rational points on the real line. So that's a particular representation of this ordinal notation system that I'm referring to. So one can do it, of course, for larger ordinals as well. And in fact, one can show, and this is easy computability theory, tells you that in fact any ordinal that is representable as a recursive or recursively enumerable or even arithmetical binary relation is isomorphic to a certain recursive subset of rational numbers. So this allows you to somewhat to consider a simpler way of representing ordinals and therefore progressions. Okay, so that would be, this seems to be a kind of solution for the representation problem. However, then the devil appears in the details, and the devil here is this problem that once you fix a system of notation for ordinals, like a subset of rationals or something, it turns out that the theories that you define actually depend not so much on the order type of a particular of the ordinal alpha as on the particular way this ordinal alpha is computed or represented. Different ordinal notation systems can give vastly different theories, can assign vastly different theories to the same ordinal. And that's that dependence is what called induced Turing's pessimism. In fact, what followed, people after Turing analyzed this situation in great detail, particularly Pfefferman and Kreisel, and what they collectively have shown is that the whole classification idea essentially breaks down because of this problem. So more precisely, there is this result. For each true pi1 sentence pi, including any consistency assertions that we so far considered, for every such pi1 sentence pi, there is an ordinal notation alpha such that the ordinal of that notation is just omega plus 1, and the corresponding theory already proves pi. So every true pi1 sentence is provable already at stage omega plus 1 in this Turing progression. Turing characterizes this theorem with a particularly pessimistic remark, typical for his character. So this completeness theorem, writes Turing, is of no value, is as usual is of no value. And yeah, so Turing apparently considered his work so far usually meaningless. You should know that by this time he already invented Turing machines and wrote his famous, by now famous paper. But for him, it is this completeness theorem, as usual, is of no value. Although it shows, for instance, that it is possible to prove Fermat's last theorem with lambda p, if it is true, yet the truth of the theorem would really be assumed by taking a certain formula as an ordinal form. So the idea to classify, to assign a certain ordinal to Fermat's last theorem will fail because it will be already provable at stage omega plus 1, and essentially we would only know that this particular way of computing an ordinal is correct by assuming that Fermat's last theorem is true. So this is just indeed a rather meaningless result in this respect. So that's the problem. What one can do, and experience showed in later years that this is possible for many natural examples, that careful selection of canonical or natural ordinal notations, not produced by the results themselves that one wants to prove using this progression, but rather if one selects ad hoc a natural system to represent ordinals in such a way that one would think. So if you want to embed ordinal omega to the omega to the rationals, take your favorite simplest embedding, and that would work, something like this, despite what Turing proved. So this idea actually produces meaningful results and allows to do this classification. And this is possible, this is shown by now to be possible for very large constructive ordinals, even though we lack a general understanding of what is actually, in general, a natural ordinal notation. So this problem of natural ordinal notation is still a problem. Proof theorists, specialists, are of varied opinions on whether it has a good solution or it doesn't have a good solution. The fact is that we don't know what it means to be, what it means for an ordinal notation system to be natural. However, we know many examples of such natural systems. So that's one of the big problems, conceptual, one can say, problems in proof theory that exist until today, since the time of Turing. Okay, now I will say a few more words on this logical complexity restriction, that relatively minor issue that was present in Turing's work, but it will lead us to the concept of reflection principles that I'm going to discuss next. So there is this fact. There are true statements that cannot be proved in any stage of a Turing progression based on iteration of consistency. How can we see this? Well, consider this artificial theory T prime. T prime is a theory obtained by adding to the theory T given to us the following sentences of the form consistency of S, where S runs through all consistent Gödelian theories. So we define what a Gödelian theory is. So if such a system S is consistent, its consistency assertion on S will be true. So T prime extends T by certain number, countable number of true pi1 sentences. So since Turing progression, starting with a, let's say, sound theory like piano arithmetic, only adds true sentences of the form con S. For theories in the progression, so obviously this T prime contains any theory of any Turing progression that we consider. So T prime is stronger than any of it. One can ask, is the theory T prime Gödelian? No, it is not, because this set of sentences con S that we add to the theory T is not computably enumerable. In fact, it is the opposite. It is co-recursively enumerable. It is pi1 definable, because in order to define this set, we need to define what it means to be consistent. Consistency is definable by a pi1 sentence. So it is a pi1 definable set of sentences. Nevertheless, one can show that, in fact, the probability predicate for T prime is, in fact, definable in arithmetic, and Gödel theorem holds for T prime as well. So one can express con T prime, and con T prime will not be provable in T prime. So that's let's say a generalization of Gödel's second incompleteness theorem for this particular case. And then we see that since every T alpha is contained in T prime, no theory in a Turing progression will be able to prove consistency of T prime. So con T prime is a sentence which is outside Turing progression. Now, to deal with it, one has to. Fortunately, there is a way to deal with it, and it is called. It is to consider reflection principles. So what we do is we define new formulas or new schemata generalizing Gödel's consistency formula, which are called reflection principles for T. So let T be a Gödelian theory, the usual one. Then reflection principles are formulas expressing arithmetical sentences, expressing that every sigma n sentence provable in T is true. Alternatively, these sentences can be also formulated as certain consistency assertions for non-Gödelian theories, for theories that are obtained by adding to T all true pi n sentences, sentences with n, pi n in the arithmetical hierarchy. So the statement Rn is in fact expressible by an arithmetical formula of logical complexity pi n plus 1. So consistency turns out to be equivalent to R0, and it is pi 1 sentence, and Rn is a pi n plus 1 sentence. And we consider them, and it is experience prove that it is in fact the right generalization of Gödel's consistency assertion to higher levels of arithmetical hierarchy. So whereas we cannot hope to prove all true arithmetical sentences just by iterating consistency, we can hope to prove them all, and in fact there is a corresponding result similar to Turing theorem for pi 1, that any true arithmetical sentence is provable in a progression obtained by iterating a suitable reflection principle of appropriate arithmetical complexity. So that's how these sentences appear. In fact, they appeared first in the work by Kleene and Rosser, and then they're studied by many others, Starsky and so on. Okay. Now I've used 1 hour of my talk for this background, but we have introduced all the classical, so to say, material and discussed everything that related to that was needed for background for, let's say, more modern things I'm going to speak about. So if there are any questions, I would be happy to make a little break and answer them so far.
By the way, could you explain more about the ordinal notation in the Turing's theorem? Yeah, this is the first question. Second question, that what is the upper bound of the Turing progression? There should be upper bound, right?
Yes. So let's go to. So what I meant was by ordinal notation was this. So we need to represent ordinals as if an ordinal is a number, let's say. How can we do it? We need to assign numbers to ordinals, and the process I suggested here was this one. Consider rational numbers. Given a well-ordering, a countable well-ordering, embed this well-ordering into rational numbers. So one can find a suitable subset of rationals which will be isomorphic to the given well-ordering with the inherited, with the standard ordering of rationals. And then, of course, we know that rationals are essentially pairs of of natural numbers or integers, and one can using pairing, one can represent rationals, and that will be the. So one can talk about elements of a well-ordering as if they were rational or numbers or pairs of natural numbers. So that's the way how we can talk about ordinals in arithmetic. Now there was this additional requirement needed for Turing progression stated here, that the ordering must be computable. And this amounts to the following requirement, that the subset of the rationals that we select is computable as a set of rational numbers. Then with any algorithm that decides whether a rational number is in ordinal or not, in ordinal notation or not, one can associate having such an algorithm. We can write out an arithmetical sigma-1 formula representing it, and then use it in the construction of T alpha. So that's roughly how it works or can work. There are other ways of doing it, but this one seems to be the simpler. As to the second question, the second question was for which ordinals alpha do such Turing progressions exist or can be defined? And the answer here is theoretically for all so-called constructive ordinals. So it is well known that among countable ordinals, there is a certain, I will write on my slide here. So this is the ordinal 0, 1, omega, etc. But all goes, so if one goes far enough, so let's depict here the ordinal omega 1, the first uncountable one. However, there is a certain ordinal which is the supremum of all computable ordinals, right? Of ordinals of those well-orderings that are embeddable as computable subsets of the rationals. And this ordinal is a special ordinal. It's called omega 1 Church-Kleene. Was first identified by Church and Kleene in their work on ordinal notations. And it is well known that this ordinal indeed has to exist. It cannot be itself computable, but is the supremum of all computable ordinals. So for every ordinal below omega 1 Church-Kleene, there is a computable system of notation, and for every ordinal above, there is none.
Okay, thank you.
So that's the answer to your question. Thank you for it, because this is good to know. In fact, it is, even if you are a student and hear about these things for the first time, but know a little bit computability theory, it's a good exercise, and in fact a very nice one, to show that such an ordinal exists and is strictly less than omega 1. So try to, I very much recommend this as an exercise or as a problem, entrance problem to the theory of computable ordinals. Okay, thank you very much. So that's it, and let's go on. Okay, so so we introduced these reflection principles as translations of consistency assertion. Now, what we are saying is, now let's start with the topic which is called reflection algebras. So this notion of reflection principle will lead us to the notion of reflection algebra, which is kind of how we see these things from more general, more abstract point of view today. So consider some minimal theory like elementary arithmetic that we dealt with, that I introduced earlier. And as we see, by dealing with progression, we deal with constructing certain hierarchies of systems, extending given system. So where do all these objects live? In fact, they live in a certain big superstructure, which I denote GEA. GEA is a set of all Gödelin extensions of elementary arithmetic. I defined what a Gödelin extension is. Modular equivalence, which I denote equivalence EA, where this one is defined as follows. So we can say that theory S is smaller than T if the following condition holds. One can say that if S is stronger than T, provably in elementary arithmetic. Whatever is provable in T is provable in S. For all X, every formula X, provable in T is provable in S. And this very fact is verifiable in our minimal system, EA. So, of course, in model theory, for example, or in set theory, in model theory, one usually views first order theories in basic courses in logic. One usually views first order theories just as sets of sentences, possibly deductively closed under first order logic. And then it is natural to define an ordering on theories like inclusion. Theory S is stronger than T if every theorem of S is a theorem of T, or every axiom of S is a theorem, if every axiom of T is a theorem of S, and set theoretic, essentially set theoretic inclusion. Here we deal with more information. For Gödelian theory, we deal not so much with theories with sets themselves, but rather with their proof predicates. So we deal simultaneously with the theory and with its representation in some meta theory, in this case, elementary. And here we require that this inclusion is provable. That's a natural ordering relation that is invariant under the properties that we are going to study. Properties that allow us to go, so we can replace one probability predicate by an equivalent one, but it does not mean that we can replace always a theory by an equivalent theory, because that's weaker than being able to formalize this in elementary. So that's the relation that we consider. The associate, it is obviously a transitive reflexive relation, pre-ordering. Therefore, the associated equivalence relation is in fact an equivalence relation. And the structure of all Gödelian extensions with this ordering, modulo equivalence is in fact a semilattice. We consider it in this talk as a lower semilattice. So just semilattice with operation, I denote as usual in lattices by a lower bound. And in this context, it corresponds to the union of theories S and T, axiomatized in a natural way. So we fix the probability predicate for S union with T in a natural way, given those for S and T. So that's the basic structure, semilattice of Gödelian extensions of EA that we are going to deal with. The reflection principles and the consistency assertions that we dealt with so far can be seen as defining certain operations, unary operations, mappings from that structure to the structure. So if we consider the semilattice of Gödelian extension of S, each Rn reflection principle defines a map. So we maps a series T to the series Rn of T, right? Axiomatized by S plus the axiom Rn of T. And that's the unary operation, which happens to usually satisfy certain good properties, among which monotonicity, if x is smaller than y, then r of x is smaller than r of y. Then there is this property of semi-idempotence. So idempotence means that double r is equivalent to single r. However, here we have something weaker, which is called semi-idempotence. R of x is less than r of x. And sometimes the operations that appear, but this is not satisfied for Rn, is the closure property, that x is smaller or equal than r of x. So the operations, the reflection principles are monotone and they're semi-idempotent, but they are not idempotent neither, and nor are they closure. Okay, so that's roughly how we can now see these things. With any, sometimes we can iterate with any operator. We can also consider its iterations, and this can be done in this semi-lattice for computable operations. So if R is so an operator R is called computable if it can be defined by a computable map on the Gödel numbers of formulas defining the extensions of the elements of GT. So this GT also bears the structure of the numbering, if you like, and then operator is computable if it is defines a computable map on GT. And then computable operators can be iterated. And that's the content of this result. There exists theories R alpha. So given an elementary recursive well ordering, and if R is a computable monotone semi-idempotent operator, then there should always exist theories R alpha or of S for every alpha index alpha from our elementary recursive ordering, satisfying the natural conditions what we would expect from iteration. So R0 of S is S, and R alpha of S is the union of operator R applied to all the theories R beta for beta smaller than alpha. So that's exactly how I would define iterations of theories in a Turing progression, as well as here. So it works in a, as you see, in a rather general setup. So one can show that once these conditions are satisfied, then each R alpha will be also computable and monotone semi-idempotent, and even unique, and even such operators R alpha are unique modulo provable equivalence in our system. So this result is just tells you that in this general context, one can also deal with general notion of iteration, which precisely corresponds to the construction of Turing progression. So this can be done rather easily in this way. And then we go back to this idea of Turing. How to measure the strength of systems, how to classify arithmetical statements according to their ordinals. And here we come to this notion, which is to the notion of pi n plus 1 ordinal, or proofly pi n plus 1 ordinal of S, denoted ord n of S. This is the supremum of all ordinals alpha, given a natural ordinal notation system, for which our alpha's iteration of Rn is provable in S. So once again, suppose we are given a system as a Gödel extension of elementary arithmetic. What we do, we generate, we take our schema Rn, our operator, our reflection operator Rn, iterated as many times as it is possible, as long as our alpha's iteration Rn alpha of EA is provable in S. The supremum of all these ordinals alpha will be denoted ord n of S. So this is called the pi n plus 1 ordinal with respect to given ordinal notation system of S. And then the conservativity spectrum of S is the sequence of all ordinals for all possible n. So pi 1 ordinal, pi 2 ordinal, pi 1 ordinal alpha 0, pi 2 ordinal alpha 1, pi 3 ordinal alpha 2, and so on and so on. So this is how we, in fact, today can characterize proof-theoretic strength. It relates not only to one particular ordinal, but rather for a family. We associate with a system a family of ordinals, each of them measuring the strength of S with respect to particular complexity class. Pi 1, pi 2, pi 3. So the system S may have different strengths with respect to each of these classes. So examples of known spectra are given here. I ignore the question how to compute them. So far, it's can be done by different means, but that's what we obtain. For example, if one takes the theory such as I sigma 1, a fragment of piano arithmetic, then it's my one ordinal will be omega to the omega, relatively small. The next ordinal will be just omega, and then just 1, and it ends with a tail of zeros, which is related to the fact that the complexity of the system itself, I sigma 1, is exactly pi 3. So the axioms of I sigma 1, they are equivalent to pi 3 formulas, and therefore, starting from number 4, we see zeros everywhere. For PA, this is not so, and the resulting sequence of ordinals looks like this: epsilon 0, epsilon 0, epsilon 0, and everywhere one finds epsilon naught. So the arithmetic is a system which is very uniform and has the same strength in every complexity. And if one adds, for example, the Worm principle that I formulated earlier to PA, then the ordinals will be different. It will be epsilon 0 square in the first case, epsilon 0 times 2 in the second, in pi 1, epsilon 0 in pi 3, and so on, all epsilon zeros afterwards in PA. This is related to the two parts of the system. Worm principle accounts for the increase here, somewhat strangely to epsilon 0 square, and the other part of PA axioms, they give you epsilon here. Of course, epsilon 0, I didn't define it. Probably I should say that epsilon 0 is the supremum of omega, omega to the omega, to the omega, to the omega, and so on, and so forth. So that's the famous proof-theoretic ordinal of piano arithmetic. Okay, so that's roughly what we, in fact, nowadays learn about a formal system by doing its proof-theoretic analysis in arithmetical complexity, by up to okay, let's go on. Time is short, so let's now, having said all that, that's the basic structure we deal with. The reflection algorithm, that's the main object of my talk, if you like. the purpose of, if you roughly have the idea what I have defined so far, then this is a message from my talk. So it's useful to study this structure. So the structure, the lattice GT, Gödel extensions of T, with the usual semi-lattice lower bound operation. 1T is a top element of this structure, which corresponds to the constant, so to say, the equivalence class of T itself. So points in that structure are series. And then there is a family of monotone semi-idempotent operations, Rn, reflection principles, that act somehow on this structure. So that's the information, that's the universe in which one can deal and study these conservativity spectra, proof-theoretic ordinals, and so forth. So what we are having in common, from this point on, we would like to say a few more words about what this structure is. So we would like to learn about, so when one encounters a particular algebraic structure, and here we see that that's just can be viewed as an abstract algebra, right? It's coming from proof theory, but in fact it is a structure which is a semi-lattice with operations. One would be interested in two basic questions, many more perhaps as well, but the two are most important. What are the identities of this structure? In other words, what are the laws that govern the behavior of the operations of our structure? What is the system of identities that it satisfies? And what is the subalgebra generated by constant? What are the, consider the set of elements of this algebra which are generated from one by applying all these operations, conjunction and Rn. And this is called the one or zero generated subalgebra, or it's a minimal subalgebra of that structure, and it turns out to be related very much to proof theory. So these are two basic questions, and let us give quickly the answer to them. So the system of identities is the system of, can be seen as a system of expressions of the form alpha turnstile beta, where turnstile is a proof theoretic notation just for the less than operation that I represented earlier. Algebraically, it's less than. So what is this reflection calculus? So we have it's an extension of a weak propositional logic. So we have propositional variables, we have constant top, we have conjunction with the usual formation rule, and we have unary operations, which are here are written just as n alpha. So n alpha means applying Rn to alpha informally. So formulas are, for example, written like that, or even we can sometimes delete this top constant because we can sort of figure out where it should be, like here. Okay. The basic derivable objects that we consider here are sequence. So we have expressions of the form alpha turnstile beta, where alpha and beta are formulas in this language. And here are the rules and axioms. So we have first group of rules saying that the relation turnstile is reflexive, top is the top, and turnstile is transitive. So it is pre-order, if you like. We have usual axioms for conjunction, saying that conjunction is a lower bound in terms of this pre-order. Most interestingly, we have principles for the operations Rn. So we have semi-idempotence that I already mentioned before. We have monotonicity if alpha turnstile beta, then n alpha turnstile n beta. And finally, two more principles. Rn implies Rm. This is N reflection is stronger than M reflection. And secondly, this is a mixed principle that sort of Rn subsumes Rm. So Rn alpha together with Rm beta implies Rn of alpha together with M beta, Rm. So that's the principles that actually hold in this for our reflection principles in this algebra. These are the main properties of this reflection calculus, first studied by Evgeny Dashkov in 2012. First result is that in fact alpha turnstile beta is provable in RC, in our system, even only if in our algebra this inequality alpha less than T beta holds. Which means that particularly that identities derivable in RC are precisely over all the identities, exactly those identities which hold in this algebra. So RC gives a complete answer to this question. Secondly, we have two pleasant properties that RC is in fact computationally simple. It is polytime decidable. There is an algorithm, polytime computable algorithm, which allows you to check whether alpha implies beta or not in this calculus. And it is accompanied by a Kripke completeness. Then there is a Kripke model. Kripke models for the logic RC, and RC enjoys finite model property. The first result is most significant of them all, but it is a consequence of something more general known from the work of Japaridze in 1986, in fact, for a very old work of Japaridze concerning the probability logic JLP. So that's these are the main properties that show that RC is a relatively good and nice system. What about this subalgebra, minimal subalgebra? Minimal subalgebra of GT, as follows from the first claim here, corresponds to the variable free fragment of the system RC. I think my time is over. May I use a few more minutes to finish, to come to something?
Or, yeah, no problem. Just take your time. Okay.
Okay, good. So, subalgebra generated, the minimal subalgebra generated by constant 1 in this lattice of theories is in fact corresponds in fact to the variable free fragment of RC. Those formulas of RC which have no variables, just built up from constants using conjunction and operations. And it turns out that this fragment is also rather nice. So let W denote the set of all variable free formulas. And then on this set we can define, of course, the equivalence relation in the logic RC, and we can define yet another natural ordering, namely the ordering beta implies n reflection of alpha. So if alpha and beta were theories, we would say here that beta proves n reflection of alpha, which in proof theory that usually is interpreted as saying that beta is much stronger or n stronger than alpha. So it's kind of relation between beta and alpha, telling that beta is that alpha and beta are not close, so they are sort of apart. Beta is much stronger than alpha. Turns out that this relation is a transitive ordering, and what we have is this theorem. Firstly, every formula in every variable free formula in W is equivalent to a word, formula without conjunction. that can be analyzed from the rules. Secondly, it turns out that the set of formulas, W modulo the equivalence relation, equipped with the ordering less than 0, is in fact isomorphic, is in fact well-founded and isomorphic to the ordinal epsilon 0 with less than relation. So despite certain simplicity of the system RC0 and formulas without variables, turns out that nevertheless the structure of W with this ordering is rather interesting. It is a well-ordering epsilon 0, which allows you to in fact view this W with this relation as yet another ordinal representation, as a system of ordinal notation. And in fact, it turns out that this system of ordinal notation is exactly the one tightly related to piano. So let's see how it works out here. Let's go for some further properties of it. So since I have not so much time left, practically no time left, let me try to do the following. I will, in a few slides, in 2 slides, I will explain how the this set of this ordering on W, this system RC, relates to the worm principle I started my lecture with. I will try to establish this connection, and then will be the end of my talk. I will point to the modern literature on this topic. Let's say on my latest papers on it, and then that will be it. So the link goes by this particular result, which is called the reduction property. So here we introduce relation n equivalence on elements of our structure. We say that 2 theories, U and V, are n equivalent if they prove the same pi n plus 1 sentences. So this turns out to be an equivalence relation, and in fact also quite proof theoretically interesting equivalence relation, often studied in proof theory in conservation results. So if U and V are n equivalent, that means that they are rather close, and the bigger n, the closer they are. So in some sense, this relations equivalence, and they introduce a kind of quasi-metric, one can say, on these on formal theories. So they introduce some kind of distance between them, and this distance is the bigger and the shorter. So a small vicinity of a system are those which are n equivalent for larger n. Okay, so that's the intuition. And then it turns out that the following results holds under certain conditions that are not so important for us, that whenever the theory U, one has that n plus 1 reflection for U is n equivalent to n reflection for U iterated omega times. So that's this result is called the reduction theorem because it sort of reduces a more complicated formula, Rn plus 1 of U, which is pi n plus 2 formula, to iterations of a simpler formulas which are only pi n plus 1. So bigger reflection can be sort of exchanged into omega many smaller reflection. And in fact, so you give sort of 1 gold coin, you receive omega many silver coins. So that's the principle. That's how we sort of view this result. However, this n equivalence relation for any n, in particular for n equals 0, it has a nice property that it preserves the consistency range. So the consistency of two consistency statements for two equivalent series are in fact equivalent. So equivalent and equivalent series are equiconsistent. And that's a very basic thing which allows us to reduce the question of consistency of more complicated arithmetical assertions to consistencies of less complicated arithmetical assertions. Okay, one particular example. Okay, is this result by Parsons and Mintz. So if one takes the theory I sigma 1, it happens to be simply the same deductively equivalent to R2 of EA. And once one applies this theorem to it, one reduces it to omega-fold iteration of R1, which in turn is equivalent to the so-called primitive recursive arithmetic. So that's that's the result that is very important for the study of this reflection algebra. And then how we explain these steps in the worm game thing that I promised. It is as follows. So suppose we have a certain worm or word alpha word in the alphabet of natural numbers. As I said, every such word can be considered as an element of W, right? W is defined here as a set of variable-free formulas of RC. So these words are particular formulas, variable-free formulas, in which conjunction does not occur, which means essentially that there are sequences of applications of our operators Rn for various n. Right? So we view this alpha as a sequence of operations of Rk for various k, finite lengths. And then we sort of look at it and see what it is equivalent to. Let alpha s denote the value of alpha in our lattice of theories in GS. For example, in GEA. Then what we see is this. So alpha s, alpha is this word beginning with n+1. So alpha s is the result of applying Rn+1 to the series U, where U is S together with the interpretation of the remaining part of the word beta, beta S. By the reduction property, so this is Rn+1 of U is a typical formula which is amenable to the reduction property. So we can sort of reduce it and conclude that it is equivalent, in fact, n equivalent, but also 0 equivalent to that sequence of to Rn omega of U, which is the same thing as the union of all these principles k-fold iterations Rnk of U for finite k. So, now, what are these Rnk of U? Rnk of U are particular operators Rnk are representable in our structure by this modality n, and Rkn of U, they correspond to particular formulas written out here. So if beta is the remaining part of alpha, then Rnk of U correspond to the formulas n beta, n of beta conjunction with n beta, n of beta conjunction with n of beta and conjunction. So this looks like a beginning finite stages of a Turing progression. In fact, they are. In fact, these are just generalizations of Turing progressions, omega many steps, but not for consistency, but for Rn, and not over basic theory EA, but rather over some theory axiomatized by beta. Important thing is that all these formulas written out here are still in W. So what we have is that that all these formulas do not go outside of W. They are still in our subordinate. And since they are in W, and we know that every word in W is every formula in W is equivalent to a word, that means that each one of them is also equivalent to a word. That's very important. Moreover, these words can be computed. It's not a big deal to actually calculate these words. Now, it turns out that these words, in fact, will look precisely as the words in our initial worm game. So these are the iterations of this initial part of the worm, that if alpha was the worm, then case element from that sequence, for example, like this one, will correspond to this element, will correspond to the three times iterated worm in the worm game. So these are exactly the worms they were read off from this process. So in fact, then the word game is just this, amounts to this. We delete 0 once we encounter a word in which the reduction property does not apply. So that corresponds to the successor ordinals in W. And for all other words in W, we apply this particular rule, which allows us to descend below and go from stronger series to lower series. So this establishes somehow a very tight correspondence between worms, if you like, elements of our algebra W, and arithmetical theories. So this correspondence is rather canonical in this context. So we read off the rules of the worm game from analysis of reflection principles, how it relates to PA. Very easily, PA is equivalent to elementary arithmetic plus full induction, but this can be replaced, and this is well known, by full reflection. So this PA is EA plus, if you like, Rn of EA for each n smaller than omega, which gives you the limit of this process of the size epsilon naught. And that's more or less how one proves, using this method, the independence of the worm principles. And one can also obtain in this way all the other results related to proof theory of arithmetic, which I am not talking here, but because I probably have to stop. So the moral from this is that using these methods, one can actually, in one go, or using one idea and very modular one, obtain all the main results on the proof theory of Peano arithmetic that are well known, including the consistency proof or characterization of its provably recursive functions, combinatorial principles. Our study goes by now far beyond that, and I must also mention that many people contributed, including Joost Joosten, David Fernandez Duque, and Fyodor Pahomov, Dashkov, and many others. And so I would like to thank you for attention, and here are my latest papers on this that you can read. Thank you very much.
I have a short question.
Hello, Joost.
Yes, yeah.
Nice to hear you. Although I don't see you, but it is nice to have you here.
Good to hear you too, Lev. I will say hello.
Hello, yes.
Okay.
I had a question. Thank you for your nice talk. I had a question. You mentioned that actually the worm principle was discovered by Hamana and Okada prior to your
Yes.
publication. So, in what context and where did it originate in their studies?
Okay, that's a good, yeah, good point. So, in fact, the story goes that when I published a preprint on worms, then Lorenzo Carlucci, a few months later, who read it, pointed me to that paper by Hamano and Okada, and they were motivated by they arrived at it very easily. In fact, Buchholz, in the study of his work on pi11 comprehension and bar induction, he developed a certain system of ordinal notations for that second order system and formulated the so-called Buchholz Hydra battle. That was essentially the generalization of the usual Hydra battle, which was earlier one of these famous basic principles by Paris and Kirby. So Buchholz found an analog of this for labeled trees and showed that it is independent of pi11 comprehension plus bar induction, something like that. Now the battle for labeled trees was, of course, formulated in a more complicated way than the battle for ordinary trees. However, the Japanese, Hamano and Okada, they decided to look at the very simplest case of that battle, namely linear labeled trees. So they took Buchholz branching trees, they considered linear labeled trees and formulated rules of the game by Buchholz. And then their task was to calculate the ordinal, let's say the proof-theoretic strength of the resulting principle. They calculated it and related it to Hydra and piano arithmetic, so it turned out to be epsilon naught. And then, surprise, surprise, the rules happen to be very similar to worms. They are not quite literally the same, but the difference is, you can say, cosmetic. You delete or you leave out 0 here and there. So I think our worms are somewhat nicer, but it's a matter of perception because they're essentially equivalent. So that's the story. So therefore, I think the real contributor here perhaps is Buchholz with his labeled trees. And then again, this is there was another paper that sort of showed that there is some strange connection between this system of notation for PA and the system of notation for pi11 comprehension. Namely, the paper by Schutte and Simpson, who studied the notion of gap embedding. So Friedman had this principle of well quasi-ordering for labeled trees, which is of the same strength as Buchholz Hydra, and it is again with this gap condition. And again, these gap conditions that they can be related to the conditions. So Schutte and Simpson considered a linear version of it, where you have essentially words again with gap condition. They showed that it is well quasi-ordering, and it turns out to be again related to our worms because using the fact that this is a well quasi-order, you quite quickly prove that these are terminating sequences that we deal with. So that was Carlucci's and Geshe-Lee's work, who sort of established this detailed connection between these things. So that was
Thanks, Lev.
Okay. Any other question or comment? Okay. I have some questions. Yeah. The Worm principle is interesting. It's a natural mathematical concrete independent sentence, and you see that it is equivalent to sigma reflection principle. And also, also I know some other natural independent sentence, such as the pH pair-Hamilton sentence, is also equivalent to sigma reflection. So this is amazing phenomenal for me. Just people have found many natural concrete independent sentences, but all these sentences are all equivalent to sigma reflection. Yeah, my question is that do you know any example of the concrete independent sentence of arithmetic which is which is stronger than sigma reflection? Because all example I know are equivalent to sigma reflection. So this is amazing phenomenal for me. Yeah.
Good question. So short answer is no. So there are many questions, many interesting examples, all of which are equivalent to sigma 1 reflection, indeed. I'm pretty sure that there are somewhat artificial examples that would be not equivalent. So somewhat artificial examples, I think, can be known. So if you are looking for stronger, so principles stronger than sigma 1 reflection, then again, I cannot give you any examples right now, but I'm pretty sure something can be stated. They will not be as convincing as a simpler example. So that's for one thing. People tried also to construct sentences that would be weaker than sigma 1 reflection by considering functions which are not provably recursive, but still slower growing than this, for example, Worm function or the Paris-Harrington function. So you can play with the growth rate of functions in such a way that you will obtain principles that are, for example, weaker than that. But it is, as I think, it's a matter of how nice these statements look like. So you can artificially distort them in such a way that they will be not equivalent. But it's not as convincing as a nice principle, so they would not be called nice in my classification, so to say. But yet another question that Harvey Friedman, of course, studied a lot is however, why? So maybe thinking about this. So, for example, consider the Friedman's principle, Friedman's finite version of Kraskell theory, for example. We know that it is independent of some stronger systems of second-order arithmetic like ATR naught, right? Finite version of Kraskell theorem is a pi2 statement, which is independent of something which is stronger than PA. Therefore, it is also independent of PA. So one can find natural pi2 sentences which are far beyond sigma 1 reflection for PA. However, they are in turn equivalent to sigma 1 reflection for some other theory, which is somehow meteorological theories above PA, something like that. Something like that is no. So this is and convincing. So in that sense, that gives positive answer to your question. However, it's not the increase of logical complexity. So it's the same complexity pi2, but higher up in the hierarchy. So to say that such principles we do know.
Okay, thank you. Yeah, I said I have a look at Friedman's work. For the last slide, the calorie. What does it tell us for the case n is more than 2? In the last slide, the important calorie.
Okay. Okay.
Yeah.
Should I explain what's this corollary? Okay. So this is a result proven by Ulschmel in I think 79 or maybe something like that, end of 70s. As you see, it relates, Peano arithmetic shows that it is n equivalent to Rn, reflection iterated epsilon naught times. That means that these two theories prove the same pi n plus 1 sentences, so they are pi n plus 1 conservative over one another. So this result essentially implies that the conservativity spectrum of PA is precisely that sequence epsilon naught, epsilon naught, epsilon naught, epsilon naught, epsilon naught, and so on. So it describes consequences of PA of any specific complexity pi n in terms of epsilon 0 times iterated reflection of appropriate complexity, Rn reflection. So indeed, n0 is level of pi 1, and it shows that consistency of pi PA is equivalent to epsilon 0 plus 1 times iterated consistency of EA. For n equals 1, we have epsilon 0 times iterated R1 reflection, so sigma 1 reflection. And iteration of sigma 1 reflection is the same thing as diagonalizing the class of probably recursive functions. So we essentially relate so the theory on the right has the class of probable functions corresponding exactly to the so-called fast-growing hierarchy. So this result for n equal 1 is a relation of probable functions for PA and fast-growing hierarchy. So you read off fast-growing hierarchy from the right-hand side, and you get the theorem from comparing the right and left-hand sides of this equation. So these are very basic and important results. So you, however, indeed, for every n bigger than 1, there is also the corresponding conservativity. For example, you can say that pi 3 consequences of PA will be the same as iterated pi 3 reflection epsilon naught times over EA. So if we had some interesting, class of combinatorial statements characteristic for complexity class pi 3, we would have obtained perhaps from this result some pi 3 combinatorial independence, but we don't have anything convincing at hand. Therefore, we don't have impressive examples like with Worms or Paris Harrington or something like that. But potentially that might actually be possible. 3 quantifiers is not yet too many, And there are plenty of mathematical theorems with 3 quantifier changes that are of interest. Therefore, I think there is some potential here to find something interesting in complexity pi3. But as far as I know, this has not been worked out.
Okay, thank you. Turing theorem tells that any pi1, 2 sentence can be proven in some iteration with a consistent sentence. But it seems that Feynman proved theorem that he generalized Turing theorem. We see that any true arithmetic sentence can be proven in some iteration with the reflection principle. My question is that what's the difference between Friedman's approach and your approach, because both of you both use the reflection principle for the iteration. Yeah, this is my confusing.
Feynman considered iterating full uniform reflection. So in fact, in his work, he took the full uniform reflection schema rather than the restriction to particle class phi n as I presented here. But I presume that this difference is not really fundamental. So that's basically, Feynman was concerned with generalizing works of Turing which are negative results. As you see, so with theorem, as stated here, I consider it, and Feynman also and Turing considered it as a kind of disappointment, right? So it's a negative result. If everything true can be proven at a specific ordinal, that means that this does not allow you to classify anything. So instead, the direction of my research, as well as the research by Schmerl, whose result appeared at the very last slide, is that despite all this, we want to obtain positive results. So isolate the conditions and situations where this approach actually does work. And for the case of, for example, this reflection principles for PA, indeed, it shows that it can work as described. Now we can, so what is going on nowadays is that we try to generalize it to stronger systems, like predicative or even impredicative theories, but indeed the whole direction of this work is exactly opposite. So we obtain positive results, like characterizing consequences of a specific system of a specific complexity by iterations of reflection principles. So that's the main difference.
Okay. Okay. Thank you. Any other questions or comments? Yeah. Anyone? Anyone? Yeah, I encourage you to use this chance to communicate with Levi. Okay, yeah. Okay, if no one, anyway, I just asked the final question that for your iteration theorem, does that theorem depend on the omega, just the recursive way of ordering?
You mean this one?
Iteration theorem.
Yes. You mean this theorem?
Yeah.
Yeah, so it works for an arbitrary elementary recursive, or you can say recursive well ordering, and arbitrary monotone semi-idempotent operator on this lattice. So that's the condition where it is sensible to define iterations. So it need not be omega, it can be essentially anything. And how we apply it, we, as you have seen later in this in the slides of this talk, we consider this system W of words as an ordinal notation system. So we consider as omega, in fact, the system W. And then apply these iterations and relate them to the words. And that's how it all works out.
Okay, it seems that your following work depend on this theorem, just alpha. But when I first look at it, it seems that whether it's better to state this theorem or follow. Just see that under some natural conditions, uniquely there exist such series are alpha with the following property. Yeah, do you think so? Because because you're following, you use this alpha, but naturally we don't use this. We need that this theorem is unique in some sense. Yeah, so yeah, so it looks to me that why you just say this, just under some conditions, uniquely there exist theorems alpha with the following property, and in the following work you use this alpha in your following slide. Yeah.
Okay, so I didn't quite get your question. So that was a suggestion to state it somehow differently, right? So could you repeat your question somewhat in more detail so that I would understand it?
In fact, it's not a question. It's just anyway some concern is that because
yes,
usually we don't only want to know that there is something with some property. It's better that we know that uniquely in some sense there exists something with some property. Yeah, because in the following you use this offer in your definition of this reflection in the algebra in your following work about the yeah. And this is only a concern and not a question.
No, let me okay. Let me try. Maybe I try to comment as follows. So in order to define these iterations, we need an ordering along which we would like to iterate. So without an ordering, we cannot define iterations. So that's the basic setup that we deal with. However, so suppose we have to analyze a theory such as PA. A priori, at first, we don't have any ordering along which to iterate. We don't know where to start, right? How do we extend it? So the traditional proof theory, let's say, did it as follows. They say, okay, here is this nice ordering epsilon naught, defined by Cantor normal forms, ordinal notations defined by Cantor normal forms. Consider it. Consider ordinals defined by Cantor normal forms. Do whatever we need with them, and then the result tells you, okay, then for this specific ordinal notation, everything works. So in my approach here, we do it in a sense in a reverse order. We don't start with an a priori given ordering. Instead, we start with this notion of reflection algebra. We consider completely abstract general structures and given by certain operations related to our reflection principles. Then we say, okay, look at this algebra. and establish some of its properties. We establish some of its properties. One of them is, as I said, this adequacy of this reflection calculus, decidability, blah, blah, certain kind of, you can say, probability logic study of it. And then we look at this variable free formulas and formulas, and discover that this structure, in fact, looks like an ordering, like a well ordering, and we can even show that it is isomorphic to epsilon naught. If we were not interested in counter-normal forms, for example, we could have said that, okay, whatever. We know that it is a well ordering and we are satisfied. It's a recursive well ordering. Why it is recursive? Because the system RC0 is decidable. As I said, it is a decidable, polytime decidable. So in fact, the well ordering that we defined here by less than 0, this one, is a polytime decidable well ordering on the set of words in the alphabet N. So that's the ordering we extracted from the structure of our algebra. And then we say, okay, why don't we use this particular ordering for proof theoretic analysis? And then we say, okay, very well. So what we obtain is this theorem stated here. I didn't talk about it, but your question led me to it. So consider this particular ordering that we deal with and iterate, consider any element alpha, any word alpha, and then it turns out that this word, its interpretation in the algebra that we deal with, the sequence of reflection, the theory defined by alpha reflection, you can say, over EA, will be the same, will be equivalent for pi n+1 sentences to the theory Rn iterated alpha times, where alpha now is understood as the element of that well ordering W. So there is a natural relation between well ordering W and the algebra, and well ordering W is just another way of looking at epsilon naught. So we relate in this way logical theories exemplified by alpha, and it leads us to this relation by Schmel, which is about PA itself, if you like. But this is much more, this theorem is much more refined, I would say, relation, because it in one go tells you about the proof theoretic strength of various systems composed of various reflection operators. So that's how it in fact works in this approach. So the upshot, the conclusion is that the ordinal notation system that we deal with here, it came from our specific way of looking at this algebra of theories, from this reflection algebra. And that's it. Then we applied to it, on the one hand, Turing's idea, and on the other hand, ideas from probability logic, and it all came together into this analysis of PA. So that's how it actually works.